Coordinate systems are a key concept in robotics. They help us to describe not only where the robot is, but where all the parts on the robot are with respect to each other. In order to represent the pose of an object in an environment, we need 6 coordinates, which are the position along the x, the y, and the z axis, as well as the rotations around those. In Webots, you have a coordinate system that is known as the world coordinate system, which starts at 0, 0, 0. And what I've done here is I've aligned the arena with this coordinate system to be centered in the center. You see the x-axis, which is red, you see the y-axis, which is green, and you see the z-axis, which is blue. And what we can do is we can look at these numbers here and actually move the arena around a little bit, and for instance move the arena up 10 centimeters along the z-axis. So you see now the position of the arena changes and goes up and down. I can also move the arena left and right, and I can also move it along negative dimensions like so. So you see now when I move along the negative x direction, I'm moving along the red arrow, and now the coordinate system of the arena travels with it, and I have this 3 solids here in the center of the arena, so you can always see the world coordinate system. Now if I increase the x-axis, I move again along the positive direction, and the same goes for the y-axis and for the z-axis. Now we not only have translations along the 3 axes, but we also have rotations. Now you see the rotations are indicated by the arrows, the circular arrows that go around the axis. So I can rotate this arena around the y-axis. I can rotate it around the x-axis, and I can rotate it around the z-axis. Now I can do the same thing with the robot, which also has a coordinate system associated to it. And now I can see that it's 30 centimeters along the positive x-axis, 28 centimeters along the positive y-axis, and 0 centimeters above z. Also here I can rotate the robot around the z-axis, and I can rotate it around the y-axis or around the x-axis. So in order to describe to somebody where the robot actually is, it looks like that I need 6 numbers. Unfortunately, that is not sufficient because it requires a convention in which order I perform rotations, and there are a couple of problems with those, which we will explain later in this course. Instead, I want you to remember that in order to describe the pose of a robot in an environment, I need to provide a coordinate system. So as I twist this robot, rotate it, and move it around, you see that the coordinate system of the robot always moves with it. So it is actually the coordinate system that fully describes where the robot is. Now what do I need to describe a coordinate system? A coordinate system are 3 vectors, the red one, the green one, and the blue one. And in this case, those vectors would need to be expressed in the coordinate system of the world. So in this case, the red arrow here goes a little bit along the negative direction of the world coordinates y-axis, and it goes along its z-axis. So the way this is done in Webots, I have a rotation field which has 4 numbers, and I can choose what is called the axis angle convention or quaternions, and both times I do have 4 values. We will talk in different lectures about how these actually work, but I want to give you some intuition. If you have a coordinate system, then you will have 3 vectors, each of which will have 3 numbers. So each of these little vectors will have an x, a y, and a z coordinate. So together that gives you 9 numbers. Now there are 3 things you need to know about coordinate systems. The first one is the vectors are orthogonal to each other. That means if you know 2 of the vectors, you can compute the third one because it's going to be orthogonal to the other 2. That means you don't need 9 numbers anymore, you just need 6 numbers, and from that you can compute the third vector. The second thing you need to know about coordinate systems is that it's sufficient, or not only sufficient, but required to use normal vectors. Normal means that each of these vectors has length 1. Now what this also means is that if I give you 2 values of a vector, you can compute the third one because you know that the length of the vector needs to be 1. And for that reason, I only need to provide you with 4 values for 2 vectors that allow you to extend the third number of each vector, but then also compute the third one. And this is why, or this is the intuition for why you would need only 4 numbers to represent the coordinate system of where the robot is. Now, in order to define the entire pose of the robot, I need to provide the rotation of the robot, again using 4 numbers, such as here, and I need to provide the translation of the robot space coordinate system to the reference frame of the world. There's a third thing you need to know about coordinate system, which is known as the right-hand rule. You might have wondered how you know the direction of the third axis when given 2 vectors. So in this case, the z-axis could point up or it could point down. Both of them would be orthogonal to the other 2. The way this works is by using a convention which is known as the right-hand rule. And for that, I invite you to take your right hand right now and take your thumb and align it with the red arrow of the world coordinate system, which is in this case that red box that you see here in the center. And then take your index finger and align it with the green block, which is the y-axis. And then extend your middle finger orthogonally to your index finger and see which direction it goes. And it will point up, such as the z-axis here. You can do this for every coordinate system that you find in Webots or in most robotic environments. In this case, we can do the same exercise for the I.5 robot. Take your thumb again, align it with the red arrow, which is the x-axis. Then extend your index finger to align it with the green y-axis. And then look where the z-axis is going to point, which is up in this case. There's also a second right-hand rule, which is to extend your thumb like in a thumbs up and then align it with the axis, let's say the y-axis, the green one of the robot, and then clasp your hands and see which direction your fingers point. And this is the direction of positive rotation. So if I rotate this robot a little so that you better see one of these axes, let's say the red one, take your thumb, extend it along the red axis and see where your clasped hand fingers point, and you will see the positive axis of rotation. Now what we can do, we can test this real quick. We go and click on the robot, and now I use the axis angle rotation and I want to actually rotate around this x-axis. So I put an axis which is the x-axis here, and I set it to 0, and sorry, the robot has already jumped. And now we can see what happens when I increase the angle of rotation, and we can see in which direction it will turn. And in this case, we would expect it to turn this way, following the arrow that goes around the x-axis. Now let's do this. And again, as we said, the positive rotation is following the direction of the arrow. The negative rotation is going counter to the arrow. So the right-hand rule is extremely important, or better, the right-hand rules that I just provided you are extremely important to understand the orientation of a coordinate system and also how rotations are affected on it.